Good morning and welcome you all to this session of the course on fluid machines. In the last class we derived the expression, an analytical expression from a very simple analysis of the movement of the piston, reciprocating motion of the piston, the expression of the acceleration head in suction or delivery pipes, and this can be written like this: the suction or acceleration head we discussed, and which is like this head H A, the acceleration head, which came like this, length by G by the area ratio, area of the cylinder and the area of the pipeline, cross sectional R omega square cos theta. Now, in the suction line, similarly head can be represented with the length of the suction pipe. So, a subscript will make the differentiation. This is the area of the cylinder, this is the cross sectional area of the cos theta. Okay. Then next is H acceleration head in the delivery side will be sorry, this is the length of the delivery pipe into this area ratio, where this is the cross sectional area of the delivery pipe, R omega square cos theta. Sorry, my handwriting is bad, cos theta. So, this is for, so expression is same, only the lengths are changed, suction, delivery and the cross sectional area. Now, from here it is clear that at theta is equal to 0 and at theta is equal to 180 degree, the acceleration head is maximum, which is change in sign. That means, the acceleration gets maximum at the two dead centers, inner and outer dead center, and at theta is equal to 90 degree, you see the acceleration is 0, H is 0. That means, acceleration is 0, whereas velocity is maximum. The velocity is maximum at theta is equal to 90 degree. That means, the movement is like this. Here you can see that the movement is like this, that at the dead centers, we have maximum acceleration, and at the middle of the stroke, that is R, this is R, middle of the stroke, we get the maximum velocity, but the acceleration is 0. And this is in consideration of the simple harmonic motion of this piston for a high ratio of L by R. Now, therefore, we have an idea that how the acceleration head is generated and how it is acted upon in the cylinder to cause a change in the head in both suction and the delivery stroke. Now, the most important part of the this reciprocating pump is an unsteady and non-uniform delivery, unsteady and non-uniform delivery. Let us do it separately. Unsteady, that means it is not same with time. So, unsteady, and rather I write non-uniform, that will be more suitable, non-uniform delivery. Why? Because if we express or show the rate of delivery, if we show the rate of delivery, if we show the rate of delivery with the crank angle theta, that is crank angle, we see from 0 to, it is 0 to 180 degree is the suction stroke. Well, it comes from the inner to outer end, and from 180 degree to 360 degree, that means 0 to 180 suction, 180 to 360 is the 0 to 180 and 180. 0 to 180 is the suction, 180 to 360 is the delivery. So, you see during the suction stroke there is no discharge, that means this is suction, there is no discharge. This is suction, so there is no discharge. 0, this is this line, rather I show the discharge as the red one, there is no, now it is already black, there is no discharge, rather this. But during this delivery stroke, which is the delivery, this is the delivery one, is very simple delivery. In consideration of this simple harmonic motion, we expect that this delivery with crank angle theta, this is theta, will be a sinusoidal, a sine curve. That means this I think we will give by different color. So, this will be like this. That means at 270 degree this will be maximum. That means we get a typical non-uniform delivery for a single cylinder, single acting pump. That means there is a one cylinder, and single acting means it has suction in one side. This is a typical diagram of a single cylinder, single acting pump. That means this is a single cylinder, it has only one suction stroke and one delivery stroke. So, during the suction stroke this is closed, there is no delivery of the liquid, but during the delivery stroke the liquid is discharged. So, therefore, suction stroke 0 delivery rate and delivery stroke there is a delivery rate, but during the delivery stroke it executes a simple harmonic motion. Initially there is acceleration and there is deceleration, resulting in a maximum velocity at the middle of the stroke. So, this results a variation in the flow velocity in the similar way, in line with the velocity of the piston, and similarly the pipe velocity only varies in the magnitude by the ratio of the area. So, therefore, the discharge also, which is proportional to the flow velocity, varies in the same fashion as a sine curve. So, you see we get a non-uniform distribution. Now, if we have a double acting, this is single cylinder, single acting, single cylinder and single acting. Now, a double acting, but single cylinder, rather I write single cylinder, but double acting. What is double acting? Double acting means it has the inlet and outlet valve similar in the both sides of the cylinder. That means, when cylinder executes a suction motion in one side left, it executes a in the right part of the liquid, it discharges it. That means, when the piston executes a reciprocating motion in one side of the piston, there is a suction created, another side of the piston there is a discharge created. So, therefore, this piston can similarly happens that piston comes the other direction, the side which was at the discharge side will be suction and the suction side will be discharge. That means, piston can take liquid from both sides and can discharge liquid from both sides. That means, both the sides there is a delivery line, both the sides there is a suction line, and the valves arrangements are like that. Sometimes ports are also given, which are designed in such a way which automatically closed and open along with the motion of the piston. So, this way if the arrangements are made on both sides, a piston is known as double acting piston. That means, it has in one stroke it has both suction and delivery. That means, in a complete cycle it has throughout a delivery. It is not like a single acting during the suction stroke, half period of the total cycle is without delivery. Okay, you understand. So, it is very simple to make a diagram. So, here what will happen, this is rate of delivery, versus the crank angle theta, the crank angle. Now, here what will happen? If we just divide this suction and the delivery like this, this is the suction. So, suction stroke means suction on one side. So, therefore, there is no meaning of suction and delivery. So, though I am writing it, this is meaningless. This is suction on one side, delivery on other side, just to make a comparison with that. That means, if I divide it, the crank angle into like this 0, 180 and 360, then we will be having a sine curve in both sectors. That means, we have a flow rate of flow velocity or rate of delivery as sine curve with 180 degree phase lag. That means, two sine curve with 180 degree phase lag. So, therefore, there will be non-uniform distribution, but continuous distribution or delivery. Here delivery is not continuous and at the same time non-uniform, but here delivery is continuous. Continuous you have a delivery, but the delivery is non-uniform. So, therefore, you see make the cylinder, pump cylinder double acting, we have a continuous delivery, but non-uniform. But this non-uniformity of the delivery will always be there, because this is the inherent nature of this type of pump, because of the motion of the piston which executes an acceleration deceleration, which is involved in its motion with acceleration deceleration. But this can be minimized to a great extent if we use multiple pumps, more number of pumps. In multiple pumps, what happens? More number of pumps are placed in parallel. As you have come to know, these pumps in parallel and series are placed in parallel and with equally spaced in terms of the crank angle. That means, total crank angle is 360 degree in its one revolution. So, a number of cylinders are placed equally within this 360 degree. Let us give an example how does it make like this thing, that let us consider a 3-cylinder pump. Let us consider a 3-cylinder pump, 3-cylinder pump, which are spaced 120 degree apart in the crank angle of crank angle. Crank has a rotation of 360 degree. So, how does it make? Let us see. Now, this is the rate of delivery, this is the rate of delivery, and this is the crank angle theta, crank angle theta. Now, let us do this way. Let us make this is 30 degree. Let me do it, then I will tell you. This is 90 degree. This is a little 150 degree. This is 210, 60 degree apart I am doing, 270 degree, and this is 330 degree. And therefore, this is, I am not writing this, it is difficult to write as 60 degree, this will be 120 degree, this will be 180 degree, because this is 60, 30, this will be 240 degree, just see that, and this will be 300 degree. Okay. All right. This will be 60, rather here you write, this will be 120, this will be 180, this will be 240, and this will be 300. This is the graduation. Now, this will be like this, one cylinder, let's this 30 and 180, it is 180. So, 30 to, it starts 30 and it goes 210, 180, no, sorry, 210. That means let us consider this as the discharge profile as we have already studied for one cylinder, which starts here at 30° crank angle as the stroke, first stroke, that is suction stroke, and ends at 210°. Okay. So, during that suction, no, delivery stroke, whose delivery stroke starts at 30°, and ends at 210° and gives a discharge like that. So, now another cylinder which is 120° away may start at 150° because of 3-cylinder pump arrangement at 150° and will end at 150 and 180 at 330°. That means, this will give. Let us consider they are of the, so say profile is same, they are of the same, 330, they are of the, my diagram, they are of the same type, they gives this 2. So, this is in phase difference of 120°, and this maximum comes at 150 plus 90, 240, and here also this comes at 30 plus 90, that means this is 120, that means the maximum is 120. That means, this is the discharge profile of the one cylinder whose discharge stroke or delivery stroke is 30 to 210 and 120° phase lag 150 to 330. Similarly, another cylinder will start 150 plus 2 is 270. So, it will go like this 270 and it will here, this will be 360 or 0, 0 means 360. This will start at 270 and if you add, this is 360, so it will be ending at 90. Okay. So, therefore, which starts at 270 will be ending at 90 for 180°, because 360, 90 and again 90, and its maximum is there at 360, because 270 plus 90 is 360 and 270 plus 180 will come to 90°, 360 plus 90. So, this is another cylinder. So, I think you have understood, if this is cylinder number 1, this is cylinder number 2, this is cylinder number 3, or you can think other way, this is cylinder number 1. So, cylinder number 3. So, cylinder number 1, cylinder number 2 and cylinder number 3, this part and this part together gives the same profile for cylinder number 3. That means, they are 120° in phase lag and all of them are giving the similar non-uniform, but a sine curve type of thing if we consider the simple harmonic motion of the piston, the rate of delivery with 120° apart. So, therefore, you see there is still uniformity, but this fluctuation is little bit reduced in this way, that if you see this, that from 30°, here you see here 30°, it starts from 30° to 90°, there is a overlap, 30° to 90°, there is a overlap. So, this part the discharge will be added, discharge of the machine 3 plus discharge of the machine 1, and if you add this, this will be like this. Sorry, my drawing is like not very good. Similarly, from 150° to 240°, this 90° difference, the scaling is also not that good. There is an overlap, sorry, this is 210°. I am sorry, not here, 210°, then it is okay. Not this 60°. Here also 30, 90, 60. So, 150, after 150 up to 210, there is an overlap between the discharge of 1 and discharge of 2. So, therefore, in between this crank angle, the net discharge will be sum of the discharge from piston cylinder 1 and cylinder 2, and if you make this, this will be like this. Similarly, here also from 300 here, not 300, sorry, this one, that is 300, yes, this is 300, 300, okay, where it cuts here, that is 300, and where this is 0, that is 300 to 270 to 330, sorry, not 300, 270 from here to not 300, 330. That means this part 270 and 30 there is an overlap. Okay, this is going up. So there is an overlap. So therefore, this will give a like this, the net discharge, sum of 2 and 3. I am sorry, from 270 the overlap starts, because here this part is there, this part, the falling part, rising part, and they are intersects here. After that this comes, so up to 330 this is there. Again I am telling, from 30 to 90 there is an overlap between 3 and 1. 30 where from the 1 starts and 90 where the 3 falls. So there is an overlap. So the net discharge will be sum of these two. Similarly, from 150 where the 2 starts the discharging, the pump 2 starts discharging, up to 210 where the pump 1 stops discharging is the overlapping, and the net discharge will be like that. Similarly, here 270 where the pump 3 starts and the 330 where the pump 2 ends in discharging is the overlapping. So therefore, if you now draw this curve, this will be like this. The final curve is like this. Final curve is like this. So final curve will be A, B, C, D, E, like that. F, if I write G, H, I, J, K, L, onward. That means this is. So in this case, still it is fluctuating. Fluctuation cannot be totally minimized, but this gives more or less a uniform flow. We can make a mean line about which the fluctuation is there. And if you have more number of pumps instead of 3 cylinder pumps, equally spaced between the crank angle, within the crank angle of 360 degree for one revolution, you get a more even or uniform distribution, but still there will be a fluctuation like that. So this way, using number of cylinders, we can reduce the fluctuation and can get uniform discharge rate from a reciprocating pump. Now, next what I will tell is the concept of air vessels. Now, to make the discharge more uniform or almost exactly uniform, I may say, and to save the pipeline in the suction side, that I will explain, air vessels, there are systems known as air vessels are incorporated in a reciprocating pump. How does it look? You see, this is the reciprocating pump. Air vessels are the vessels closed in one side, contains water and the air above it, which is at a higher pressure. And these air vessels are connected in suction side and delivery side as close as possible to the pump cylinder. That means this should be as close as possible to the pump cylinder in the delivery side. This is in the suction side. This is air vessel for suction pipe. This is air vessel for delivery pipe. Now, these air vessels acts like a flywheel. What is the function of a flywheel? Flywheel store energy, extra energy when it is given to him, and it has to be removed from the system, and it supplies extra energy when it is required, and it stores energy and gives energy. It can do so by its huge inertia. So here also this stores extra energy and gives extra energy by this compressed air. Now when the air is compressed by the movement or the inflow of water here, it takes energy. That means when there is an excess water in the pipe and it has to be reduced, the water comes here and the air gets compressed. Similar is the function for delivery pipe line. And when water will be required in the pipeline, so water will be given by this, by the expansion of the high pressure air. So therefore this air, when it expands, releases water or in terms of energy, and when it is required or when it is compressed, then it absorbs energy. So therefore compression and expansion of the air in the air vessel releases water or takes water from the line. How does it work? You see, when it is attached to the suction line, then what happens that in the acceleration head more water is required in this suction line. So, okay. So, this water will come here and this will be given by here. So, that the rest part, which is the major part of the suction pipe, since it is placed close, is flowing mostly with the same amount, same flow of water. The flow of water is kept uniform, it is not changed, but the acceleration at the beginning, due to acceleration head, more flow is coming from this. And similarly, in the deceleration part of it, the water goes to there. So, therefore, the large portion of the suction pipe, which is not clear from this figure, is associated with a uniform flow, and therefore, the chance of cavitation is reduced. Only the fluctuation in pressure and the flow velocity or the discharge rate, which is inherent to the machine, takes part only in the short column or short length of the suction pipe between the air vessel and the pump cylinder. Similar is the case for discharge. When the initial acceleration is high and discharge rate has to be more, so this releases water and goes like this, and the similar thing happens at the end of the discharge period. So, therefore, the rest part of the delivery line, just like the similar to suction line, gets uniform discharge because of this air vessel. It gives additional air water required the initial part of the delivery stroke because of the acceleration head, and similarly takes water to reduce it. So, therefore, this part gives the uniform flow discharge rate because of this air vessel, whereas this fluctuation takes place only here. You understand? So, maintain a uniform discharge rate, the additional thing is taken up by this. That means, when the initial acceleration is there, more discharge takes up by this part remains uniform. When that discharge is less, it gives less discharge at the rest part of the delivery stroke, this is being released. So, therefore, you see here also the rate of discharge remains constant here. So, additional discharge goes here, initial part, and where the discharge rate is less at the end of the delivery stroke, then the water comes through this. So, therefore, this part of the pipe, the discharge is fluctuating more at the initial part in consideration of acceleration rate and less at the latter part of the delivery stroke in consideration of its deceleration. So, but in both the parts, this acts to absorb and release water. First, it takes water in the initial part, the extra water, so that this discharge rate is not hampered, and at the end it gives water, deposit water to for makeup, so that this discharge rate is not hampered. So, we get a constant discharge and constant pressure in the rest part of the delivery line. So, this is the precisely the function of the air vessels, to make the constant discharge at a constant pressure in the discharge line, to make the suction line to for a greater part of the suction line to have the constant discharge without fluctuation of pressure, and this is the function of the air vessels on two sides. So, from there we can summarize that incorporation of the air vessels reduces the possibility on the suction side, reduces the possibility of cavitation, and we can use a higher length, more length of the suction in the suction side pipe length, and we can increase the pump speed, because the pump speed is related to the minimum pressure in the suction pipe, that is the pressure E here, the pressure E, the minimum pressure in this cycle. So, minimum pressure can be increased, that means we can reduce, we can go to a lower minimum pressure, so that you can avoid cavitation, and length also you can increase. And this incorporation of air vessels gives the advantage that extra power required in providing the extra discharge in times in case of additional acceleration heads in the initial part of the delivery stroke through a long delivery pipe is saved. So, it is the saving of power, and another thing is the constant rate of discharge, which is more important and which is not usually obtained from any reciprocating pump without the air vessels. Even a number of pumps, there will be a fluctuation, but it will be relatively more uniform. So, this is the function of the air vessel, and this ends today the lecture on reciprocating pump, hydraulic pump, and today we close our lectures on hydraulic machines, that the machines using water or any other liquid. And next class we will start discussions on machines using air machines. Okay, thank you.